Hey, what's up, guys? Okay, so in this video, I want to talk about this Bernstein Vazirani problem, and the reason why I think previously I make the same video, but this time I think I am much familiar with the setup, so I can like hopefully present better version. Okay, so this gives you the oracle separation of this BQP and PPP. So this similar as Simon's problem. Okay, and so basically this kind of and also related to the idea called fluoridation, which is very interesting topic. Because our idea is that the problem setup is the following, right? So you have a hidden function, which is Boolean function. Okay, so some Boolean function. And you already know that f of x is x dot s. Okay, so this is u as the dot product of the f2, right? So you can imagine that, okay, so ss are both in f2, f2 to the n. So this is basically s1, s2, s2. However, this is just sum of the XOR sum, basically sum of the just in f2. Okay. Okay, so f, and your goal is to find s. Okay, so the classical. So for the classical one, that obviously one can show that if you IP 1 0 0 0, right, this then in, then I will get s1, right, and I can put f 0 1 0 in, then I get s2, right? Because this is one dot with s1 and f 0 0 0 1, I get s in. Okay, so you just take n steps, and actually you can prove that you need n steps to find s1 to sn. Okay, but for the quantum, and we only need once. We only need once. Okay. So the basically one can just use the Curie quantum Curie model. So the model is very simple, right? So this model just tell you that basically there's operation, right? So your operation is the following, right? So if you start with ai to the x or ai to the I, and then there's a UF, right? Usually people will write it as a control U. But for a Curie model, that I can just say UFX on it, right? So I can just say AI to be -1 f of I. Okay, I can just directly say that God just give me, right? God give me this UF, and so for any state that I can apply. Okay, and the Curie complexity asks about how many times of UF that I need to Curie. Okay, so I need to use this UF, but how many times that I'm okay. Okay, so the idea is that you only need one Curie, and the proof is very simple. Okay, so you start with 0 1 to 0 0 0 product of n, and go to n Hadamard. So basically this is, let me just write. So this is basically as this. Okay, so just for me it's a lazy. So you have UF, there's a UF, and H, N, and just major. That's it. Okay. Okay, so let's try to prove this. Okay, and the only important formula that we need to remember is that if hx on hn enter x on Hadamard x, that you write x is a bit string, right? So you can prove that square root 2 to the n summation of -1 x y dot y and y. So this y from 0 1 to n. Okay, and once we have this, there's enough. Okay, so after this step, this is just the this, right? So 1 over square root 2 to n, and x from 0 1 n. Also, after this UF, you get 1 over square root n x minus 1 sx x from 0 1 to n. Okay, and after final step, that your states become 1 over 2 to the n, because remember there is a 1 over square root 2 to the n here. You get x 0, 1 to the n, y 0, 1 to the n, and minus 1 sx, and minus 1 x, y, y. Okay, and you can just collect it. So let me just collect it. So you get 1 over 2 to the n, y from 0, 1 to the n. Let me just rewrite the coefficient plus x, y, y. Okay, so I just measure y. Okay, and obviously that, so we just need to compute this, right? We just need to compute this. But this term is amazing, right? This term is basically this. This term is just basically summation x 0, 1 to the n, and minus 1 x plus y. Okay. And but this is minus 1 to x, right? So this is factorizable. So you can write this as a product of x1 up to xn, and then minus 1 xi, and times si plus yi. Okay, because this is factorizable, right? You should just write everything down. And but obviously that sorry. This is incorrect. Basically, it's this product, right? And this is xi. So now xi is 0, 1. Okay, and then we total have nth term, right? So it's so just I. Okay, so so this term is like minus 1, 0 as 0. Right, sorry, usi plus yi plus minus 1. Right, so x1 is 0, you get 0, and for x1 is 1, you get s1 plus y1. So this is 1 plus minus 1, s1 plus y1, right? And in order for this sum to be 0, non-zero, then for each I, right? Since it's products, right? So in order for this sum to be non-zero, for each I, this term must be non-zero, right? This term must be non-zero. And in order for this to be non-zero, the s1 plus y1 must be 0. Right? Notice that we are in F2, right? So this means that y1 must be equal to s1. Okay. So this means that for each I, right? So this means yi needs to be si. Okay. So what I want to say is that this actually force s must be equal to y must equal to s. Okay. Okay. So you can imagine this is ys. Okay. So y need to be the same as s. Okay. So now I can just rewrite this sum to be 1 over 2 to the n summation y to the 0, 1 to the n, and then now this term must be y as s, right? Right, because oh sorry, not okay. If this term is 0, non-zero, then this term must be equal to 2, right? Because this is s1 plus y1. If it's 0, then it's 1 plus 1 must be 2. So there will be another factor which is 2 to the n, which is here, right? Because we are n of them. Okay, so amazingly, this term just be s. Okay, so simply speaking is that if you directly measure this, then you will get s1, s2 up to sn. So you just get s. Okay, so you just need 1. Okay. So obviously that for you can say that if you only take, okay, so for quantum you just need 1 Curie. And for classical, you will take any Curies. Okay, so okay, and so basically you can say that if you set however, right, you can prove that you can find this is basically the separation from BPP and BQP. Yeah. Okay. So yeah. So this is Bernstein Vazirani, and this is interest related to this for equation, and I will give the simplest model of relation in the next videos. See you guys.